Well, a few months ago, I prepared one or two video segments on the use of sensors in the Catia's finite element module, but I realized that maybe I should discuss those at more detail and more depth, and that's what the plan is today for this particular segment. Now, let me remind you that when you do FEA in Catia, you get tree looking like this, and then at the bottom of the tree there is a line or a branch called sensors. If you put the cursor on it and right click, you get a menu here, and the particular uh, area that we're interested in is these sensors at the bottom of this menu that we got. Okay, so there we are. Today we're going to be discussing in the context of a very simple example: local sensor, uh, global sensor, applied load sensor, internal load, and reaction sensor. All of them. Okay. Now, I want to do the problem so that simple enough that you don't get bogged down with the parts and things of that nature. So here is the geometry that actually I'm going to be making. So it's a cantilever clamped at the left end and loaded on the face with a total force of 100 pounds on the right hand side. The dimensions are given here. Now, also, because I want to show you what happens when you create these sensors, I'm going to make a big enough mesh, for example, a mesh of size 2 inches, so that you have very few nodes and very few elements, so that we can actually track what's happening in the situation under consideration. Okay, so let's go ahead and make this. On the vertical plane, I will sketch a 1 by 1 square square and dimensions 1 inch by 1 inch, obviously, and that's going to be the cross section of the cantilever. So that's going to be 1, and this is going to be 1. Say OK, exit, and we pad it by 5 inches. 5 inches, so that'll be 5. Okay. By the way, just so that you can see what the coordinate system are, obviously 0 is right here at the left end, but I will create a coordinate system here right there so that it actually places it for me in that way so that I can track down things later on. Okay, let me also hide these planes. Hide, hide, hide. Okay. Why don't we go ahead and apply material to this thing? Let's make it out of steel. Metal, although for the purpose of a purpose that you have in mind, that's really irrelevant, but that's okay. We're going to make it out of steel. Okay, now we are ready to go to generative structure analysis. Remember, analysis and simulation, generative structure analysis. Static analysis, it puts a mesh of that size for me, but immediately I'm going to make that thing a lot bigger. Let me show you first of all what we have if we use this mesh. Right click, mesh visualization. The mesh is going to look like this, but it's too many nodes and elements, so I'm going to change the size to 2 inches. Linear, I'm going to use linear. Make sure it's linear because it's parabolic, although the video tutorial is okay, but the interpretation, you have to work on it a little bit differently. So anyway, mesh visualization right here. Okay, very coarse mesh. And now I'm going to hide this generic element that we have here. Hide it. Okay, good. Now, deactivate the mesh. So there is my part. We're going to clamp the left side. So clamp the entire face. Okay. And on the right side, I will apply a force, total force, distributed force of 100 downward. And there we are. Now I want to remind you, when you use this force, when you use this, what it does, it takes the total force and divides it by the number of nodes on that face that you pick. And on that face, let me remind you, there were only 4 nodes. There was top left corner, top right corner, bottom right corner, and bottom left corner. These are the only forces. So each one of them will carry 25 pounds, as you can see it in this screen. All right, so let's go ahead and run it. Yep. Well, why don't we save this thing first? File, save management, analysis, save as, desktop, July 4, 2020. So both the part and the analysis are going to go into that folder. This is not a big deal. So we're going to run it. Very simple problem. And it is done. Okay. So we can look at the deflection. There's a deflection. Don't let it bother you, because what happens is that there's a few elements. It's going to be ugly, but that's really not the point of this exercise. Okay. You can always set the scale maybe to make it look better. There we are. Actually, this is as good as it gets. Okay. Because we have very few elements, this is how the structure is going to look like in deformation. Bends basically. Okay, so let's put it back where it was. Deactivate this plot. I'm going to deactivate this plot. Okay, now the order that I'm going to do these things, I'm going to follow the order in my slides. First of all, global sensor. What does it mean when you create a global sensor? Well, global sensor is a single number which reflects this entire structure. For example, you put the cursor here. You say create global sensor, and it says, okay, what do you want actually to be recorded? What do you want to be kept track of and recorded in your tree? Well, for example, I may want maximum displacement, and do another one. Look, as soon as you did that, it appeared here. You can also change the name if you want. So the other one, I'm going to perhaps see what the mass is, because the mass of the object is for the entire object, so it's a global entity. So where was that thing? Global sensor. If you want, there's the mass. Okay. And in fact, if you expand this thing, it tells you that the maximum displacement is this much, which obviously is at the right end, and the mass is about 0.04 slinch. Slinch is this weird mass unit in when you use inches and pounds and things like that, but that's really doesn't matter. Okay, so I'll leave this thing expanded like this. These are, so you got the idea of what the maximum what the global sensor is. In fact, why you do these, not only to see the numbers, but later on you can use these variables, these things in your maybe you want to write a few lines of code that it says, okay, maximum displacement divided by perhaps the force is going to give you the stiffness, transverse deflection of it. So these can be used for post-processing purposes. In fact, if you click on f of x and you say, okay, show me, for example, where is this thing recorded in my tree or in my list of entities in the model, is right there. So for example, you can say add a formula, and then use this, or you can use the math. Okay. All right. What is the next thing in? By the way, notice that when you do a global sensor, it doesn't ask you where, because it refers to a global entity. Okay, what's the next one? Now I want to call about applied load sensor. So the first thing is to do, I'm going to do it 3 times. Load sensor, I'm going to pick a point down here, and later on I'm going to pick an edge, AB, and pick an edge, where's the other one? The top face. Okay, so I'm going to do three problems. Okay, so let's see. Now, put the cursor there, right click, apply load sensor. Well, now before I do that, let me tell you what the reaction sensor is. Reaction sensor is only at the reaction that you may have, react at the restraints that you may have. For example, reaction sensor, let me call it reaction. Get the reaction sensor. There's only one restraint here. I can take it from the tree or from the screen and then say update. So it tells you what is the reaction of the restraint. So obviously it's 100 because there is minus 100 pound applied on the right side, and the reaction at that support is 100 up. Okay, there's no big deal. And the moment is the moment about x. If you look at the moment about x, it takes 100 multiplied by the moment arm, 500 poundage. Okay, so fine. We also have this. Okay, good. So we talked about the reaction sensor. That's very simple. Actually, it was done in the other tutorials too. So let me collapse these so that I can reach the top easier. Right click, applied load sensor. When you do that, it says, okay, where do you want the applied load sensor to be placed? Well, if I do this corner point, for example, and then say update, needless to say, it shows you minus 25. Minus 25 down. And what that means is that on the support that I picked, which happened to be that vertex, on the support that I picked, what is the load, external load that was applied? Remember, it was 100 on 4 of them, 4 nodes, and each one divided by you take 100 divided by 4, you get 25 and downward, because you're applying the load on the face. So it takes that value divided by 4 nodes on that face, 4 nodes on that face, and places it at each corner point at each node. And in this particular case, as our support, we pick just one vertex, so you're going to get minus 25 down. Let's try now and see what happens when I select an edge, the vertical edge. So let's get this. Say OK. By the way, these are all recorded in the tree. If you want, you can see it. This is the one point that I picked. It's a good idea to give these meaningful names, for example, vertex B, etc. But I'm not doing it. Right click, applied load sensor, and I select this edge, and I say update. Okay, so what happens on that edge, if you look at the screen here, on that edge, there are 2 places where external load is applied, the top and the bottom, 25 and 25, that makes it 50. And so minus 50, you can see that. So you can see that minus 50. If you look at the moment, you're going to get a moment of 250, what is that, 251? And let's see where this thing comes from. About x is 250, about x is 250, about the y is 25. So moment about x, if you look at it, each one of these forces will have a moment about x-axis, this 25 times 5, and this 25 times 5. And when you do that, it's going to be 250 with a negative sign. If you look at the moment of this force, applied force about the x-axis is negative. So the moment, where's the moment here? The moment came out to be minus 250 about x-axis. Okay. If you look at the about the y-axis, it's going to be 25 plus 25 times the moment arm, which is 0.5. So 25 times 0.5 plus 25 times 0.5, and that's going to be it's going to be let's see now, it's going to be 25 about the y-axis as we expected. Now if you look at the force, it's going to be minus 50 downward, and that makes sense because at these 2 corner points, top and the bottom, we have 25 applied. Okay. Now, if you do a third one, for example, if you go and say, okay, give me a applied load sensor about this face, on this face, update. Let's look at the force first. Minus 100, we know that 100 was applied to the 100 was applied to this face right there. You can see that. So the force downward is going to be 25, 25, 25, and 25, which is 100 downward. And by the same token, you can take the moment of these about the x-axis and the y-axis, and you're going to get these, and the z-axis, and you're going to get the numbers here. The only one that has a moment about is about the x-axis, and it's going to be basically a total of, well, think about it as 25 times 5, 25 times 5 plus 25 times 5 plus 25 times 5, etc. And then that's going to be about the x-axis is going to be 500, right? 25 here times 5 plus 25 here times 5, etc. That's going to give you minus 500. And nothing about x and nothing about y and z axis because they can't. All right. So now that we realize what these things are, let's go to the applied load sensor. Not applied load sensor. Sorry. I'm not going to do the top one, but you can do it yourself. It's easy. Yeah, I was planning to do, instead of selecting the face on the right side, which I did a minute ago, I was planning to do the face on the top. And of course, the numbers are going to be different, and you can work it out yourself. Now we're going to go create a local sensor. So I'm going to do it 3 ways, exactly what I did. So vertex B, edge AB, and the top face. Remember, I forgot to do the top face, so I took the side face, but here I'm going to do the top face, no problem. Okay, so create load sensor. Let's go there. This is the first one we're going to be doing. Let's go here. Put the cursor. Right click. Applied load sensor. Right there. Applied load sensor. Okay. I'm sorry. Not local. Load. I meant local sensor. Local sensor. Right here. Local sensor. Right there. Okay. It says, all right. What is it that you want to actually see? Okay, so let's say we want to see the displacement displacement vector. Okay, so fine. This appears here, and it says, okay, now tell me where. So double click, put the cursor here, left click on it, double click, and then it's to say, what is the support? The support is this bottom point right there. Okay, and on purpose, I'm going to give this thing a name. I'll call it at B, vertex B. Okay, it was vertex B, right? Yeah, vertex B. And then it says, okay, well, we know what you want to create. It was actually displacement. I'll call it displacement B. How about that? Displacement at B. Okay, so it's a displacement that we picked. Now, what is it that you want to show? Well, if you want to show all the components, all the component displacement in X, Y, and Z, you can do these. Or if you want to do just, maybe 2 of these, just select the other 2. Select the appropriate item. So let's say all of them, all 3 components. Okay. Now, if we say OK, this is still it needs to be updated. So put the cursor there, right click, update sensor. It says, well, I have to do some running, some calculation. We say fine, and notice that now it's no longer in the mode that it says update me. Now, because if you double click on this thing, you can't see much. That window opens up, so we don't want this. I don't want to see this. But what you can do is you can say, okay, right click, export data. Export the data. In other words, this thing that you created, why don't you put it on in an Excel file for me? So we say here, it says, where do you want it to go? Let me put it in the same folder. And that was, I think, July. Let me see, what was my folder here? It was July 4, 2020, right there. Put it in that folder. Let's give it a name. I'll call it at B, displacement at B. We say OK. Just give it a second. Now, if you go to that folder that I had right there, there's an Excel file there, right there, and it gives you the information that you asked for, the displacement in X, Y, Z direction at vertex B. These are the coordinates of the vertex B that I picked, 0.5, 0.55 and minus 0.5, and these are the displacement values. So you can use it for whatever purpose you have in mind. Let me do another one. Save. Let's go back here. And let's do another one. So you put the cursor here, right click. You say, what was it? Local sensor. Again, displacement vector. For example, on that, okay, say okay, and then it wants you to go and pick it. So let's click on this, double click on that. The support is right here, this edge, and the name that I'm going to give it is displacement on AB. Where's that? On AB. Okay. So we say again, what components do you want? If you want all of them, that's fine. And then uh, uh, say OK and update. You say fine and export it. So in the same folder, I say on AB. On AB. You say OK. Okay, so if you go back to that folder, you have another Excel file, and it gives you 2 points, 2 nodes, because on AB there are 2 nodes, and each one of them will give you the displaced values, okay? Maybe you want to use it for a certain purpose, okay? Now, if you notice that here, let me close this. Let me close that. Okay, if you go here, if you go double click on this, it says basically all 3 components, and there are 2 points on it, but you can also say, for example, give me the average of those 2 values as opposed to maybe individual displacement at those nodes. So let me cancel that. Let me cancel this. Let's create another one. Let's create another one. Create local sensor. Again, displacement. Okay. I double click on it. I'll say average on B. Average displacement on B. If that is the case, then here you say, okay, you have to do some post-treatment. Post-treatment means that give me the average. Now, if you select create parameter, this number will also appear in your tree. Notice that these guys, there was nothing on the tree that you could show. But if you want a parameter to be created, maybe because it's a single value, so select this, okay? And the support is that edge, and you say okay. And notice that you have to update, and now it gives you the value. If you want, you can also export it for some reason. Export data, average on B, average on B, on AB. So obviously in that Excel file, there's going to be a single number, which is going to be your, let's see now, average on AB, which is the average displacement of the points A and B. Hang in there. Which one was average on AB? Maybe I, okay, so the Excel file is still the same thing. However, in the tree, I was under the impression it prints the average in a single Excel file, which is not the case, but it gives you the average displacement right there. Average displacement, see that? The average displacement. This is not going to go into Excel. It looks like when you say, okay, export that, it's going to just take the values at the nodes A and B, displacement at nodes A and B. But if you want the average, maybe you want to write a few lines of code, see, to do something, then you can use this parameter. If you click on f of x and use this, it actually tells you what the average value is, and you can use it for writing code or whatever purpose you have in mind. Let's do the last one here in this group. So create local load sensor, again displacement, say OK, and let me double click on that. For the support, select the top, okay, and well, first of all, I want something. I want maybe how about maximum displacement? Create a parameter, okay, and did I pick it? Yep. Say okay. Okay, and then you have to update it. I didn't change the name, but I could have. Okay, so maximum displacement is going to be at that top node. If in fact you can also let me actually change the name of this thing. Let me change this thing. I'll call it on face AB. AB. What is that? AB. No. ADEF. 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 And I want maximum value, and that's going to appear on the tree after you right there. This is the maximum value is this number. You can see that. But if you want to export the information, in other words, notice that there's 6 nodes on that top face. Export data, I'll call it on ADEF. EF. This is not average anymore. I thought it was going to do the average for you, but in fact, it's going to give you 6 displacements. You want to check that? Okay, where is it? Right there, right there. It's not going to give the average. It's going to give the value at the 6 nodes. Right there, 6 nodes. 1, 2, 3, 4, 5, 6. Because if you look at that face on the top, you have 2 nodes here, 2 nodes there, 2 nodes there. That makes it 6. Okay. All right, we're almost done. The last thing I want to do is about this internal load sensor. Let me just quickly remind you what does it mean, internal load sensor? If you have the same problem and you make a cut with a plane, that plane has a normal end, and on it there is something called a traction vector. Okay, so this traction vector, if you look at your strength of material book, is given as the product of stress tensor, stress matrix, which is that's why it's called internal, times the normal the normal vector. Okay. So if you take these Tx, Ty, Tz and you integrate it over that, this is the stuff that you do in a maybe second course in stress analysis. You're going to get the traction, you're going to get the forces acting, the resultant forces acting on this face that you do. The unit of these are the stress, you can see that, but when you integrate it, you're going to get force components acting on that face. So that's really what internal, I don't know why we need something like this. Probably it's useful to some people, but anyway, so let's put the cursor there and say create, what is the local one? What was it called? Internal, sorry, not local. Internal load sensor. And once again, it says where. So I mean, I'm going to take this top face. Okay, I you know, you can make cuts in principle, but I'm going to make that top face. So, and then you say update, and it gives you the forces acting on that top face. in the XYZ and moment in the XYZ. Let's see if it makes sense, by the way. So if you look at the forces acting on these, you can, if you look at it, you have, remember, on that top face, there is 25 and 25 down. Okay, if you look at the forces, 25 and 25 down, and then there are reaction forces on that side which are going to go up, and that uh, internal uh, load sensor is going to balance those. Now, if you want to exclude the applied load sensor, you select on it and update. Of course, it's going to, change the numbers. So I really don't know why this is so useful. Why this is useful, but anyway, that's what it does. So it's based on uh, giving you the the forces acting on a particular support, may it be a face or whatever, uh, based on the stresses calculated. I think that'll do it. It took longer than I expected, but it probably demystifies some of these sensors that you want. And by the way, I don't think you can actually export this. Yeah, you can't export it. You can just show it here. Okay. Good luck.